So welcome back, everybody, to DeepRob, and in particular, welcome back to Lecture 5. So the topic of today's lecture is going to be where we now are getting into neural networks. So we'll still sort of be focusing on the topic of image classification, but the concepts that we're talking about now in terms of how we set up our new neural network classifiers are going to extend then to the other types of machine learning problems and robot perception problems that we look at for the rest of the semester. So before getting into the neural network content, I think I only have one slide today on an administrative update. So just a reminder that Project 1 has been released. Today marks the halfway point from when it's due. So it's going to be due a week from today, so January 26th at midnight. All the instructions are online. Hopefully everyone's gotten started. The autograder is online, and we made some updates based on some of our distance calculations. We're using float 32s. So all of the results that you see now should all be correct. They should have automatically been updated from our incorrect tests for the first kind of couple days. Feel free to post in EdStem or email us if you're having issues with the autograder. And then the one other announcement I want to make is with regard to the quizzes. So we're going to, in terms of like notifying everyone when there's a quiz, we'll make sure that we always say in at least one lecture section ahead of time when to expect a quiz. So for example, last lecture on Tuesday, I didn't say that there was going to be a quiz today. So there was some confusion about that, but there is no quiz today. So don't worry about if you didn't take the quiz or didn't see one on Gradescope. Next Tuesday, there will be a quiz, and next Thursday, there will be a quiz. And to make it clear on the announcements, what we'll start doing is posting on the website calendar which lecture sections in advance there are quizzes. If we're not announcing things, though, just as a general rule, it's not intentional. We're not trying to conceal the information and make it like pop quizzes. That's just because in trying to get the lectures and the projects and EdStem and answering everyone's questions, sometimes the core staff gets overwhelmed. So I apologize for the confusion, but we appreciate your patience with us. Okay, before moving then on to today's topics, are there any administrative questions that I can answer? So we'll go ahead and get started. So a brief recap of what we've been talking about in the last few lectures. So we've been looking at these linear classification models, right? So between the softmax classifier, the SVM classifier, and we saw how we could describe a scoring function that would try to score how likely or how confident maybe one image is for belonging to a particular class using those different linear classifiers. And so in order to then decide which of our potential parameter settings of those classifiers were preferred or not preferred, we had set up a loss function. And so that loss function was expressing our preference over the various parameter settings that we could potentially have for our classification models. And then last lecture, we started looking at how we could start to train these using stochastic gradient descent, and also how we could regularize our models to avoid overfitting to the data sets that we're working with. And so today what we're going to be looking at is a new class of classification models, which are neural networks. And these are going to be the kind of like the foundational model from which we're going to build up our deep learning models as we go along. So even starting from today, we'll start talking about what you could call deep learning, where we'll have deep neural network architectures. So to understand why it is we don't want to just stay with the linear classifiers that we've been looking at, right? Because we did see like linear classifiers have some benefits, right? So for one thing, we can interpret from the different geometric viewpoints or the algebraic viewpoints how these models are performing. The downside, though, is that linear classifiers for high-dimensional, very complex data sets, like the ones that our robots often deal with in perception tasks, they're not complex enough. They can't represent enough of the types of decision boundaries that we'll want them to be working with. So for example, if we consider like the geometric viewpoint, we saw that linear classifiers are forced to sort of separate the space of possible classification boundaries into linear boundaries. So if you have data that follows some nonlinear distribution of classification, so for example, on the figure on the left, we're showing this data which you could not write down a hyperplane that would separate the green and the blue class. Linear classifiers will never be able to perform to 100% accuracy on these types of data sets. And so for visual data, generally speaking, is a very, very complex problem for classification, and so it's one where linear classifiers suffer. And so what we want to start to think about is how it is we could potentially transform this original space of input into maybe a transformed space that would make the problem easier for our classifiers to to operate within, because this ultimately is what neural networks are going to be doing. So in this kind of contrived example, we could imagine taking our original space of input data, which is these two-dimensional points, and we can imagine transforming them out of Cartesian coordinates into polar coordinates, where now the data we could see is linearly separable. So if we applied this feature transformation, we could actually kind of manually construct a linear classifier that could classify this otherwise complex data correctly. So this is a nice property of performing a feature transformation. The problem is that when you start moving into high-dimensional spaces like images, it becomes less and less intuitive for how a human engineer or a human kind of feature engineer could start to perform these transformations. And so what we're going to want to have are models that could learn how to perform these transformations to take highly nonlinear data and transform them into a space where they could potentially be like linear classified using a linear model. And the reason why that's powerful is that if you were to then consider what this linear classifier in a transformed feature space is really doing, it's actually performing nonlinear classification in the original input space if you were to sort of back project your classification boundary from the transformed space into the original space. And so this ultimately is what our neural networks are going to be building up to be able to do. So from this kind of contrived, kind of trivial example, it's very clear that being able to perform these feature transformations would be a powerful tool. And it's one that historically in computer vision has been used to great effect. So what we're going to look at on these next set of slides are a few kind of older school approaches that were state of the art even as recently as like 10 years ago for performing image classification. But since then, deep learning has outperformed that. But the main takeaway from these approaches that we're going to look at is it's kind of illustrating the power of transforming from this like low-level pixel space into these higher level or transformed feature spaces. So the first approach that we'll talk about is if we were to take our image that our robot's going to perceive and describe it using transformed features, which is a color histogram. So imagine we took every single pixel in the image. So the one that's illustrated here is this pixel on the kind of like the leg, or let me move my cursor, on the leg of the frog. If you were to look at what color that pixel corresponds to, you would map it, let's say, into the discretized bin of blue, and then you would add within your color histogram like a +1 for that pixel belonging to that discretized bin of color. So if you were to imagine doing that for every single pixel in the image, what you would have as a result is this histogram over the possible discretized color values, and this would be a transformed feature to represent what's in the image. And so this is one approach you could use to try and describe like what features at a slightly, like according to this transformation, belong to this image. And you could then potentially train a classifier on those. But just using the color histogram generally did not result in very good performance for our classifiers. So instead, one approach that was used and is still used today to describe the features within images is a slightly more complex feature representation called the histogram of oriented gradients. If you're interested in like so we're not going to go into like the low-level details of this algorithm because it's not used very commonly in deep learning now. If you're interested, the computer vision course, so 442 and 542, they do go into more detail about this. The reason though that we're covering these is just to give a sense of what was the state of the art before deep learning entered the picture. So what the histogram of oriented gradients is going to do is it's going to try and use information about how the intensity of the pixels within your images changes locally to describe what features are in the image. So what you would do is you would go at every single pixel within the image and you would compute what direction the gradient of the pixel intensity is changing towards. So you'd calculate just like a gradient in pixel intensity at every single pixel in the image. You would then divide the pixel into, generally, they were 8 by 8 pixel regions. And for every pixel within your 8 by 8 region, you would compute a histogram over a discretized set of directions that the gradient could be pointing to produce then a set of features to describe the overall image. So what that would look like, so this is like on the right-hand side of the slide is a visual representation of what these histogram of oriented gradients would look like if over this set of 8 by 8 kind of windows over the overall image. So each of the white lines within the black and white image on the right-hand side is showing the kind of count within a particular direction of the gradients for one of the histograms for one of the 8 by 8 windows. So the main kind of benefit of doing this is you have transformed from like low-level pixel information into potentially like a slightly higher level representation of what features correspond to different portions of the image, right? So you're losing a lot of information in this transformation, but potentially you're making it so that a linear classifier, if it was given the histogram of oriented gradients as features instead of the raw pixels, could potentially do a better job at classification. But again, this would be a handcrafted approach, right? So a human had to decide that, okay, the direction of how pixel intensity is changing could give some indication about what is in the image. And so in this case, for example, like one reason that that's potentially useful is like if we were to like look at like this lower left-hand corner of the screen, so on this leaf, right, there's this very strong direction of pixel intensity, which is pretty well aligned on the leaf. And so that gets represented in this histogram of oriented gradients by the fact that in those regions, each of the 8x8 windows, the histogram for each of the 8x8 windows shows that the directions of highest pixel intensity change correspond to those directions that like on the leaf's pattern. So potentially it would be easier for a classifier to try and use the fact that there are these kind of consistent directions of intensity change to try and classify that as like, let's say a leaf, as opposed to just the raw pixel values, which in this case are green, but for another image would be blue and would have like a lot more, would be like a much higher dimensional space. So like another few examples of how this information in the transform feature space corresponds to what we see visually. Like you can see like in this upper right-hand corner of the image, there's very little, little edge information. There's not a strong change in intensity of the pixel values. And correspondingly, there's in that portion of for the histogram that corresponds to that window, we can see like the histogram is just small for all of the possible directions of change. So indicating that there's really not many features there that our classifier should be paying attention to. And then similarly, one interesting part is for like the region around the eye of this frog, which is a circle, like the eye of the frog in projection is a circle. We can see that the corresponding histogram of oriented gradients shows that there's a strong pixel intensity change for essentially all of the directions in the discretized set of directions of change. So in some sense, that feature, the fact that there's like a strong pixel intensity change for all of the directions, could be used by a classifier to signify that, okay, the pixels within this window correspond to maybe like a circular shape. So it's a slightly transformed version of the pixel features. Okay. So building on top of that then, another approach that was like handcrafted and used to actually some effect was the bag of words features. So the idea behind this approach was you would take in some data set and you would randomly sample patches from this data set. So for example, like let's say we had a data set that just had 2 images. And so this is moving towards a data-driven approach, right? So in this case, you're not just having a human engineer use no input data, they're just using their knowledge of pixel features. Now what you have is the human engineer is going to take some set of images, extract patches randomly from this set of images. So you can see like we have some patches from the car up in where my cursor is up here, some patches taken from the frog image. And then we're going to build from those, we're going to cluster those patches using like a k-means clustering algorithm, and then use the cluster centers that we produce to represent this code book of possible features, which is on the right-hand side, which is then ultimately what we'll use to try and represent unseen images using like a feature transformation. So the first step, though, is just build the code book. So this is what the human engineer would do, right? So they would get these images, randomly sample crops, patches from the image, and then based on how those patches are clustered, we could produce a set of code book features which would represent like commonly occurring low-level patterns that we see across a variety of images. At that point, then, if you're given some new image and you want to encode it into a feature space, what you could do is you could evaluate how each of the features in your code book, how strongly those patterns are represented in this new image. So what you would do is you would take each code book feature and then take an inner product with all the possible windows in this new image to generate what we can think of as a histogram. Let's see where my mouse is, down here, for each of those codebook entries. So in this example, if we look at the codebook entry up in the top right here, so this codebook entry is in some sense describing like a strong change along the direction that corresponds to like a diagonal facing kind of like the upper right of our screens. And so that we should kind of recall is similar to the pattern that we saw in this frog image for the leaf pattern. And so if you can imagine taking an inner product between that codebook feature and the windows that overlap the leaf pattern down in the lower left-hand side of the frog image, we would expect that the corresponding histogram for that codebook feature, which is where this cursor is here, would be strong. And because we see a lot of that feature, that pattern, in this particular image. And so this bag of words transformation is yet another approach that we could use to try and handcraft some domain knowledge into a feature transformation, but in this case using some elements of a data-driven approach. It turned out in practice that generally speaking what would work very well is if you wouldn't just rely on one of these feature transformations, instead what you might do is combine them. So maybe what you would do is you would first take your histogram of color intensities, you would concatenate it with your histogram of oriented gradients features, and also concatenate it with your bag of word features to produce a very, very long feature vector to represent each image before trying to apply a linear classifier. Question? Right. So yes. So the question was in both bag of words and also the histogram of oriented gradients, if we find that there's like locations in the image where there's a strong gradient, like a strong change in pixel intensity along certain directions within the image space, that if we find those kind of features, then that would correspond to like one of the like a component of our resulting feature vector. So it's independent of the, so we wouldn't necessarily add weight to that gradient. The gradient would just be a computation. So like in this image, what you could do is you can calculate the gradient in pixel intensity along the x and the y dimensions of the image. So that's just like a rote equation. Like you can use a numeric approximation to like take the change in the vertical direction of pixel intensity and the horizontal, and you can do that for every pixel. So that's just like a deterministic function. What then the histogram of oriented gradients is trying to do is say, okay, within each window of the image, like for example, like within this blue window of the image, I want to now count how many of the pixels within this 8x8 window have a gradient that falls along a certain direction, and then I'm going to treat that as a histogram. So you're sort of counting up how frequently you see gradients falling along possible directions. And then the more frequently that you're seeing those gradients would add weight to the corresponding feature that represents. Right. It's similar to an edge detector, right. And then there's a slight difference, though, in the bag of words case, where the bag of words is not necessarily looking for edges or for gradients, or for large gradients. But if it just so happens that your code book, based on the sort of training images or this data set of images that your human engineer has access to, if it just so happens that that edges are commonly occurring within your training set, then that might be a feature within the code book, like in this example code book that's shown here. But it's also possible that that you're not going to always be looking for edges with a bag of words. So the bag of words is no longer like making the assumption or like adding the intuition that a human engineer would that edges are useful for classification. It's trying to learn it from data, or trying to use data to. Right. So in the histogram-oriented gradient, so in this example, we're saying that the window's 8x8. You could take a multi-scale approach to describe like your images. So you could use a window size of 2 by 2 or 4 by 4 or 8 by 8, or you could use all of those and combine. You could concatenate the resulting histogram of oriented gradient features that you get for the different window sizes. So that's yet another hyperparameter that the engineer would have to try tuning with to see what model has like the best performance. And so it's possible that if you have some knowledge of what data set you're trying to use these features to represent, the window size, you might be able to build in some intuition, right? So if you know that the particular data set you're trying to work with and represent in feature space has sort of frogs that are, or like has objects that are centered within the image and are generally taking up the full size image, you might want to use a larger window size based on that knowledge, right? So that's sort of how these handcrafted approaches would work. You would try and use your intuition about the specific data set you're using to build in knowledge into the algorithm. And so that can work well if you have a constrained data set and if you have highly skilled engineers that can do these feature transformations and use their knowledge to implement these feature transformations. But on really complex data sets like ImageNet, where you have like 1.3 million images that are of all sorts of different natural scenes and backgrounds, it becomes really hard to use intuition across all of those possible images. However, these sort of handcrafted approaches were the state of the art even as late as 2011. So the winner of the 2011 ImageNet, which was right before deep learning started winning ImageNet every single year, was one of these approaches based on these feature transformations. So what they would do, if you're interested, the paper is cited on this slide. So they would combine like low-level feature extractions. They would use SIFT features, which is another variant of like a low-level feature transformation, combined with the color histogram, and then also another, like a few other feature extraction tools which we didn't talk about, but if you're interested in the details, I'd refer you to the paper, so these ones. They would concatenate those together and then train an SVM on that final large feature vector that's trained with stochastic gradient descent, and that was actually the best model at the time for doing image classification. Ever since, though, data-driven approaches in the form of deep learning have been winning consistently and pushed the performance to a lot higher accuracy. So if we think about how this sort of human handcrafted image feature-based approach would compare to our neural network approach, which we're going to be talking about, they're actually quite similar. So they're similar in a sense and different in a sense. So for the feature extraction approach, right, we have some image that's going to go into this what we could say here, it's a yellow box, but that represents the function that a human engineer would build to represent this image in terms of higher level features. Those features then go through some final classification function, which is like the scoring functions that we looked at in the what was lecture 3. And finally, then we would get a final score for each of the possible classes that we're trying to predict. And then we would maybe train that final layer from data, right? So that final linear classifier we would train from data. In contrast, what the neural networks are going to do is replace as much of the human feature extraction as possible. So instead of having these functions that are implemented by the human, instead what we're going to do is we're going to have just a very large and deep neural network that will be trained completely from data. So it's going to be responsible for learning both the feature extraction component of our model and also the final classification component that will produce a score for each of the classes we're interested in. Okay, so we've been talking about neural networks. So what is a neural network? So in some sense, we actually have already seen a neural network. So our linear classifiers we could think about as being a single layer neural network. So let's say that we have some input vector. So our input vector x comes from of dimension d from the real number set. And we have this function, which can be a neural network, f of x, will output a vector of real numbers of dimension c. So where c is the number of classes that we're trying to classify. So what we were looking at before in a linear classifier setting was f of x being some weight matrix, w, here, multiplied by our input image as a vector x, and then we had that bias term as well. So we had then the learnable parameters as this weight matrix of size d times c, and then our bias vector of dimension c. Now what we're going to have is we're going to extend that idea to multiple layers. So if we imagine first having a 2-layer neural network, what we're going to do is we're going to treat it as follows. So we'll still have first, we're going to take our image x, multiply it with the matrix of weights w sub 1, and add a bias 1. Then we'll pass the result of that through some nonlinear function. So in this case, we're taking element-wise max between 0 and the result of just this first linear function. And then the result of that nonlinear activation function, this max operation, is going to then be applied to a second set of like a second linear transformation. So we'll have then a second matrix W sub 2 that will transform this output of the activation function, and then a second bias term as like the final operation. So this now is our definition moving forward for a two-layer neural network. So in this case now, instead of having one set of learnable parameters, W and B, we now have two sets. So we have W1, B1, and then the second W2 and B2. So the thing to point out that's worth pointing out is that for the second set of learnable parameters, so W2 and B2, the actual size of those is not going to depend necessarily on the input data. It'll depend on how many output classes we want, right? So our output is C. But now we have this hidden dimension, which is what's being produced by this first layer. So that hidden dimension is going to control essentially how many features are being output as a result of our first application of the learnable parameters. And so our second then function, like our second parameters W2, is going to depend on that size. And the way then we can start to think about how the two-layer network is performing the task that a human engineer would otherwise perform is we can think about it as the first layer is extracting features. So the first layer is acting just on the raw pixel values and trying to extract some intermediate features, whereas the second layer in this two-layer network is what's actually performing the final scoring operation. So the second layer then we can think about as the actual linear classifier that we're going to use to finally make our classification decisions. But this idea then can keep extending. So you could have your one-layer neural network, a linear classifier. You could have a two-layer, three-layer, and so on, where for every additional layer that you're adding, you're just sort of recursively applying this same high-level structure. So you'll just add on, in the case of a three-layer network, you'll add on one more weight matrix as the output of your second activation function, and then one final bias term corresponding to that third layer. And so you can see that you could start to sort of chain these together to eventually form a deep neural network. And so that's where the term deep learning comes from, is we're going to start training these deep networks from training data. Okay. So one way, though, that's useful once you start working with these is trying to visualize what the actual network architecture looks like. Because if we were to keep writing out these deep neural networks in functional form, we all of a sudden have like many variables that we have to keep track of in terms of the learnable parameters. And so sometimes when you're trying to convey a network architecture to others, like for example in the form of a paper, it's more useful to graphically display what it is that the network is processing as opposed to just in algebraic form. So for the rest of this lecture, what we'll be looking at is the form shown here. So the way to sort of view this is each of the blue columns represents a vector of numbers. So that's either our input image, so for example, X, or one of the intermediate, what we would call hidden layers, right, which in this case is denoted by the H. Whereas then the white portion of this figure, so W sub 1 and W sub 2, that corresponds to the parameters that are being used to transform from one of the feature vectors into a second sort of intermediate or final feature vector. But conceptually, we're describing the same thing. So what we're showing here is a two-layer neural network. So algebraically, the output is shown in this equation. And graphically, then, we're just showing it in this figure. Any questions so far on what we've seen with the two-layer neural network definition? OK. So one way then, like another way to kind of interpret what the weights are actually representing, because the weights are what we'll refer to as fully connected, we can start to interpret what the weights are actually representing. So for any of so let's take weight matrix W sub 1 as an example. If we consider element at the position I comma j of that weight matrix, in some sense that's giving the kind of effect or the importance of the term in the input x sub j on the output h sub I. And so the sort of way to interpret that is if you imagine the row within W sub 1 at row I, that row of the weight matrix is going to be used as an inner product with the column vector x to produce the final output at h sub I. So that's one way you can kind of think about what each of the elements within the weight matrix is actually doing. It's going to be processing a specific dimension from the input of that layer within the network, and it's going to be affecting just a single dimension of the output of that specific layer in the network. So you could do the same reasoning, for example, on the second weight matrix. So if you wanted to know what does element I sub j of the second weight matrix, W sub 2, like what effect does it have? Well, it's representing the effect of output S sub I, which is our final score for the ith class, based on the intermediate layer, which is input to this W sub 2, to this second portion of the layer, from the term H sub j. And so if you naturally then sort of expand this line of thinking, we'll sort of realize that these networks, as we've defined them, are fully connected in the sense that every possible dimension of the input can affect every single dimension of the intermediate hidden layer, and every single dimension of the intermediate hidden layer can potentially affect every single score that we're giving as final output. So we would refer to these style of networks as fully connected neural networks, because at every layer, the input and the output of each layer is fully connected. And also, you'll see these referred to as multi-layer perceptrons. So like a bit of like a historical note. Actually, Chad, do you want to help me talk about like the historical note just briefly about like perceptrons and how there was the AI winter caused by?
I'm not going to say too much, but you know, as we talked about in the first lecture, we had the neural networks that we see, the perceptrons that we're using, were envisioned or were made by Rosenblatt at Cornell in 1950s, around the same time that artificial intelligence became its own thing through the Dartmouth Conference in 1956. The original neural network, the original perceptron, was not electrical. It was like electromechanical array that would take in very simple images and then be able to classify them. And so there was a big battle about should AI be, you know, search-based methods and all the things that we thought of as AI and sort of, you know, up till about the mid 2000s. Or should it be neural networks? And they just sort of went back and forth. And so there was a book called Perceptrons that was written by two big AI people, Marvin Minsky and Samuel Papert, that just completely savaged neural networks and said that they were terrible and you shouldn't use them, and here's all the reasons why they were bad. And you know, that sort of set back neural network research for a while. And typically what people do is they kind of overpromise. Our AI is going to do everything and it's going to be amazing, and nobody can ever live up to that hype. Even the current neural networks that we're thinking about now might not be able to live up to all of your expectations. It's not an issue of capability, it's an issue of expectations. And so when you overhype and underperform, people start to figure it out, and that caused what we call AI winter, which really sort of inhibited funding. People did not want to give funding to artificial intelligence for certain periods, and then they come back and they say this is really awesome and amazing. And they're like, oh, you're overperforming and it didn't go well. And so you know, so AI has sort of been in this sort of wake-sleep cycle for a while. But recently, you could make the argument that since 2011 and the introduction of the artificial intelligence systems that we're seeing now, they're based off of neural networks. The search-based systems that you're seeing that you use every day for Google Maps and all sorts of other searches around the web, that both of those ideas actually are valid and true and great. And are producing great things for us, but this model has actually been around for some time, and so is that enough history?
Yeah.
All right, I can say more.
No, that's great. So the thing then that's worth thinking about is the fact that in the first iteration of the perceptron, they were limited to one layer. They weren't thinking about multi-layer perceptrons, and so by adding multiple layers and by increasing the depth of these neural networks, that was part of what led to the sort of the increase of interest once again in this approach, and ultimately the recent success. So, given that we have now defined this architecture of a neural network, now we should start to try and contrast it with just the standard linear classifier that we looked at before, right? So before we had just the linear score function, and now we have these two layers. So what the linear classifier was doing, if you recall, and as you're seeing in Project 1, is it was using one template per class to try and determine what the score should be for some new image that it's trying to classify. In contrast, what these neural networks are going to be doing is building up a set of features that are being used internally to decide on the final score. So we can use a similar approach of trying to understand what, we could think about them as like templates the neural network is using by first looking at for the first layer of the network, we could take the parameters and treat them as a set of images similar to how we did with the templates from the linear score function. So what I'm showing here on the left-hand side are the 64 filter banks that were trained from the data set that we're working on in Project 1. So trying to classify these household objects. And once again, so these are features taken from the first layer of a two-layer neural network. So in some sense, what these neural networks are doing is it's using the first layer as a sort of one template or like a set of templates for no longer one template per class. And then the second layer, based on how well each of these possible templates aligns with some input image, then that second layer is going to use those intermediate hidden layer output to finally decide on a score. And so it's worth kind of thinking about what these hidden templates are, or what these initial templates are actually kind of representing. So one thing that's cool to see that we couldn't achieve with just the linear score functions templates is now we can have different templates for different modes within the data. So the two examples that I'm highlighting in red, so I'll point out with my cursor, it's the one up in this region of the overall filter bank and down here. Visually, to me, these both look similar to the Campbell's soup can, which is one of the objects from the data set. The distinction, though, the reason why I'm pointing out that these are multiple modes of the data is that the can, or this filter bank down on the lower left hand, this appears similar to what the Campbell's soup can looks at if you're viewing it from the front facing of the label. The second filter bank, to me, appears like it's trying to represent the Campbell's can if you were looking at it from the back, where you have like the nutrition information, because there's more white pixels on the nutrition information and less red pixels. So that, in some sense, is indicating that we're capturing in the multiple modes, which are the different poses that we might be looking at the can from. Another example of this multiple mode behavior is if you look at these two filters, so the one in the down, like in these two lower portions of the filter banks, these both to me look similar to the mustard bottle, except under different illumination conditions. So you remember from the second lecture, we talked about how illumination changes is one of the issues, one of the challenges that image classification often has to overcome. In the linear classifier setting where you have one template per class, we did have, if I go back like 2 slides, we did have one template for the mustard bottle, but it wasn't able to capture multiple modes of like these different illumination changes. So by now allowing our network to have multiple templates that it could potentially use within its classification decision, we're starting to capture these more complex patterns in the data set. Additionally, though, while you can point out some of these kind of interpretable filter banks, there's a lot of filter banks here that are totally uninterpretable to me by my reasoning. So I mean, I've highlighted some of them, but in fact, really it's most of the features here are not like visually linkable to one of the output classes, right? So a lot of the filter banks here have a lot of green, for example, and none of the objects in our data set are green. But somehow the network learned that it was useful to still use those filter banks within the final decision of the scores for its predictions. So some of that interpretation is useful, but we can't always rely on interpreting or like kind of like introspecting the inner workings of these models when we try to understand what they're using for their decisions. So that's a two-layer neural network. The sort of powerful approaches and the ones that are winning ImageNet now are what we call deep neural networks. So as the name suggests, the idea is that instead of having just 2 layers, we're going to increase the number of layers within our network until it's by some amount deep, and then we're going to call it a deep neural network. So there's no official number at which you can say, oh, this was a not deep neural network and now it's a deep neural network. But just the idea of we keep adding layers, we keep making these networks deeper, and they're going to represent sort of higher and higher level concepts and hopefully achieve higher and higher accuracy. So as terminology, when we say depth, we're referring to how many individual layers there are within our network, so along the horizontal portion of the diagram. If we say the width of a particular network, we're referring to how many like what the dimensionality of the intermediate hidden features are within the network. And so you can sort of see why it is we would want a visual representation is because as we keep adding features and keep adding layers, the algebraic form becomes more and more complex. And so it can be harder and harder to convey what the idea is within a particular architecture if you're describing it algebraically. Okay, so one important thing that we should sort of talk about, which we mentioned, is this notion of what we were calling an activation function. So within our two-layer network definition, as shown on the top right of this slide, we do have a question. Thanks. Yeah. They can have, yeah, so the question for those online was, in this diagram, we're saying that the width of the layer, it's shown as constant for all of the layers from the first layer on. And is that common in practice? So I would say for most state-of-the-art approaches for image classification, typically the dimensions of the filter, like how many features you use in intermediate layers will change. So they're not always going to be constant. That gets in, like we'll talk more about that when we get to convolutional neural networks. Sometimes it's more useful to have maybe many features at the low level of the network and then fewer features as you get to higher and higher level concepts deeper in the network. But that's not always true. It depends on the data set. So it's a good question, though. Not always is the width the same. You can dynamically change the width. Yeah. Yeah. So, okay. Other questions? Okay. Okay, so we brought up this idea of an activation function when we defined our two-layer neural network, which was this max operation that we were applying to the output of our first linear operation. And we call this an activation function, or alternatively, sometimes it's called an activation function or the output of an activation function. And that's typically what we're referring to as the hidden layer output. So the max operation would be included within that, like H or H sub 1 within the previous diagram. And one of the most common, probably the most common activation function is this max from 0 versus the output of your linear operation. That's alternatively called the rectified linear unit, or ReLU for short. And this really is, this is really the most common activation function. So when you're starting out and you're trying to implement a new network, generally speaking, it's recommended that you start with ReLU before trying others, but there are others that we'll consider. So one question you might be kind of having is, why do we need this, right? Like, why didn't we just define a two-layer neural network that has, as it's kind of shown in this second portion, that just has two different weight matrices and two different bias vectors, which would be much more conceptually simple, right? Like, why do we increase the complexity by having this nonlinear function? Any thoughts on why it is we would need, why it is we were interested in having this activation function? In the back? Yep, that's exactly right. So this definition that we have on the lower portion of the screen without the nonlinear activation function is exactly a linear function. It's just we've changed how it is we're representing the parameterization. So if instead of if we just sort of distribute the operations, what we would see is we still have some weight matrix multiplied by our input vector, and then we have some column vector which would represent a bias. So without that nonlinearity, without that max function, we're going to be left with still a linear classifier and all the issues that we talked about that come with linear classifiers and their limited ability to represent nonlinear data. So that's the motivation for using activation functions. So I mentioned that ReLU is the most common, but there are others. So depending on, generally speaking, most commonly what you'll do why you'll substitute activation functions is for what distribution of output you want at your final layer. But this does apply to intermediate layers. So sometimes you will try, as a hyperparameter, changing the activation functions you use, but you'll always want to use nonlinear functions in order to capture the fact that we just talked about, which is we want our models to be nonlinear. So there's these 6 that are highlighted on this slide are common, but ReLU is generally considered the default choice for models that you'll be working with. And so once again, so why Why would we want to potentially use like a sigmoid activation? So like let's consider that if we wanted our output to be represented or sort of considered to be a probability, the sigmoid function will output values that are constrained to be between 0 and 1, which we could then treat like a probability. Whereas ReLU, because it's just 0 for any values that are less than, where the input is less than 0 and then it's linear after, will not produce values that are constrained to be between 0 and 1. So if you wanted your output to be treated like a probability, you would use sigmoid and not ReLU. So that's some of the intuition that might go into your choice of activation functions. Okay, so now that we've set up this idea of what a neural network is in terms of like algebraic form or visual form, now we should start to think about how it is we could actually go about implementing one in code. So on this slide, this is a very concise representation of the code you would need to set up a neural network. In fact, it's less than 20 lines of code to set up our neural network. Yeah, question? If you want the output of your network to be between 0 and 1, so if you wanted it to be a probability, in the case of classification, like we're talking about, then yes, you would use sigmoid. But if you don't necessarily want that constraint, then you could use a different output activation function and then potentially treat your scores differently for your final classification decision. Right, exactly. I mean, now this is coming from more of my, because I'm very interested in probabilistic inference. I would say I'm somewhat skeptical about whether sigmoids trained with gradient descent really are probabilities, but we can treat them like a probability for this discussion. Yeah. Another question behind? Can you use softmax as an activation function? Yes. So let me think. So softmax depends on. Yeah, you could have a softmax layer, and it would be both. Yes, you could. Yes, you could. You can interpret it as probability. Yeah. And then just like as a side note, the reason why I'm saying like I'm being careful with my words because like a probability, there's like some great classes here on random or probability theory and random variables that if you're interested in that you should take. Generally speaking, I use the word probability to refer to observable events, and so I think I'm skeptical of whether like an output number that's just scaled between 0 and 1 represents the probability of observing a specific event out of a set of measurable events. But that's another course. So yeah, for our discussion, it's a probability if it's between 0 and 1. If you want to talk about at office hours about probabilistic inference and how they relate to deep neural networks, I'd be happy to do that. Okay, so we've set up neural networks. So it's worth kind of thinking about how it is we would implement them. So the steps, the kind of core steps we would need to start implementing these in code are first we have to initialize the weights, and not shown on this slide would be like the biases, but all the parameters we need to initialize. So you can see here, for example, we're initializing for a 2-layer neural network of our 2 weight matrices, and where the dimensions of the first weight matrix are going to be the input dimension of the data, and then our chosen hidden dimension. And then for our second weight matrix, it's going to be the hidden dimension, which is going to be treated as input to the second layer. And then finally, the output dimension for the overall network. And then in this case, we're going through all of a set of training examples, or in this case, maybe it's just during inference. So we're going through a set of the kind of examples of images, and we're computing here a loss. In this case, it's a sigmoid activation with an L2 loss, and then the gradients based on that chosen loss and activation function, and we're even training the network. So we're even having a stochastic gradient descent step down here where we're updating the weights based on the gradients as calculated above. So for some of the upcoming projects, I think referring back to this slide will become useful. But we're just trying to point out that it's worth starting to think about how we would implement these in code, and for simple networks, it's not too difficult to actually start implementing. Okay, take a drink. Okay, so So now what we want to talk about is I want to kind of come back to that concept we were starting today's lecture with, which was trying to understand how these relatively simple neural networks that we've been talking about can start to actually perform the feature transformations, which we said was very important for classifying nonlinear data. And so to do that, we're going to be looking at these diagrams here, which I'll go through and kind of explain how to visually understand them before we start looking at this topic of space warping. So let's consider that we have just a single layer neural network. So it's just a linear transform of this form. So we're going to have some hidden feature space that is output from just a linear operation. So we're going to have our weight matrix W multiplied by our column vector X. Let's say it's a two-dimensional input. So the two-dimensional graph that we're showing here corresponds to the first dimension of X along the horizon and the second dimension of X along the vertical. And then our output, let's say, hidden dimension is also of dimension 2. So this transformation then can be thought of as a scoring function. So what we're showing then, let's say that we've trained our model or we're given some initial weight vector. So what the two lines then are showing are the level, so this red line and this green line, not the dashed, but the solid red and solid green lines, those are showing what we call the level set of scores that are being predicted according to this linear transform. So what that means is if you were to take, let's take the red line for example, let's say that that's class 1 or hidden, like hidden dimension 1. Actually, because of the next slide, let's say that's hidden dimension 2. The red line is hidden dimension 2. Any point in the x1 and x2 position, so any kind of horizontal point that falls along this red line will have a corresponding score for that h2 dimension of 0, anywhere along this red line. And the same goes then for the green line. Any x1, x2 point that falls along this solid green line has a score for the hidden 1 dimension of 0. I kind of flip forward, but let's keep focused on the left plot so I can kind of explain it. So the other then fact to point out on these plots is that then what the arrow so like this red arrow and the green arrow, what those are showing is the direction of increase for those hidden dimensions. So if we move along the direction of this red arrow shown on the dashed line, that corresponds, so any points that move along that direction in the x1, x2 space will have a correspondingly increase in the score that's produced for the h2 dimension. And then the same kind of discussion goes for the green arrow. If we were to move the x1 and x2 points along that direction, the score that's being produced for the h1 will increase. That's what's being shown in this plot. The reason I'm pointing that out is because we're going to now do some reasoning about how space is being transformed by this linear operation, so it's worth making sure everybody understands those concepts. One kind of interesting fact is the actual, like those directions, like this red arrow, the direction that's being indicated by the red arrow, that we can actually think about as it's the row of the weight matrix corresponding to the h2 dimension. So in that case, it's like the second row within the W matrix. The green arrow would be like the vector representation of the first row within the weight matrix. And then also to point out, because there was this question that came up, I think 2 lectures ago, the bias term is actually represented as the height at where like x1 and x2 is 0. It's essentially like the height of like this level set. Like it's the amount of score that is produced when the input is exactly 0 for each of the 2 classes. Okay. Before we go on with the space warping, any questions on how to interpret these, like the diagram on the left-hand side? We will get to that. Yeah. So at this point, though, in discussion, let's say we're not using any activation function. So it's just a linear transform. Yeah. Okay, great question. What happens to a data point that's above the intersection of these two lines? So let's start thinking about that. So to think about that, let's imagine, so the short of it is that we can say for sure that any point that falls into that region A will have a positive score along the h1 dimension of the hidden space, of this transform space, and also a positive score for the two-dimension of the transform space. So if we're now going to start thinking about what this feature transformation is doing, let's imagine considering space in terms of the hidden dimensions h1 and h2. So what we can confidently say is that any points from this original input space that fall into the region demarked A will correspondingly be somewhere here. So they'll have a positive value for h1 and a positive value for h2 based on the fact of like where they're falling with respect to this level set, or these two level sets. And then we can do the same kind of reasoning for the other quadrants. So let's take the region B, which falls somewhere on the negative side of the score function for the green dimension, so h1, but still positive for h2 based on where it falls. So it's, it's on this positive side of the level set for h2, but it's on the negative side for the green dimension h1. And then you can do the same kind of reasoning for the other two quadrants for C and D. Yeah, question? Right, exactly. We're sort of doing this change of from the input feature space into this transformed feature space. And the reason why that is useful to think about, so in this case, this is just an affine transformation, but once we start adding activation functions, we'll get into nonlinear transformations that'll be useful. So let's think about, like, once again, before adding an activation function, what this would look like with individual feature points. So let's say that we have this data set that we're trying to classify into yellow or blue. So the inputs for this classification problem are these two-dimensional points within x1 and x2. And you can see how if we have a linear classifier, this data is not linearly separable. So if we try and train a model, it's going to, we're not going to be able to draw some hyperplane, even within the transform space, that actually linearly separates the data and would correctly classify it as belonging to yellow or blue. And that's because this input data, once again, it's a nonlinear classification problem. But let's start thinking then instead about what would happen if we were to add a nonlinear activation function. In this case, we'll talk about the ReLU activation function and how this problem would change. So if we add the ReLU activation function, which once again is just taking the max of either 0 or whatever the output of our linear transform is, the first thing we can do is we can say that, okay, for the region of space that was positive for the score of h1 and positive for the score of h2, so this region A, it will be transformed in the exact same way. So it will still correspond, like every point in that original input portion of the space will correspond to some portion of the transformed space in this quadrant. But things start to change when we think about the other quadrants. So for all the points that are in quadrant B of the input space, they're still going to have a positive score for h2, but they have a negative score once they're output from the linear function for h1. And so correspondingly, once they've been transformed through the ReLU, they're going to have some positive value for h2 still, but then they're going to sort of be like collapsed, right, onto the 0 point of h1 by that ReLU function. And then the same kind of ideas go for the other portions of space. So like this, all the portion within quadrant D of the input is going to be collapsed onto the 0 portion of h2. And then for quadrant C, they're all going to be collapsed exactly onto the origin of the hidden space because they're negative for both the score of h1 and h2. And so the reason why this can be valuable is if we start thinking about, in terms of individual data points, what's going to happen, the ReLU function is doing this collapsing operation, which can actually make the data linearly separable in the transformed feature space. So this non-linearly separable data in the input space is now linearly separable in feature space. And so that's really the value of the activation functions, at least graphically, in this low-dimensional example. And so you can imagine then if we start working with much more higher dimensional data, where there's maybe much more nonlinearity than just what we're showing on this trivial example, how these activation functions can be really crucial to get good classification performance. Question? Yeah, so right. So the question was, if instead of this example, if we went back to like slide 3 or slide 4, where we have like actually maybe like a full circle, let's say, of like one class is sort of a full circle around the other class, would we actually, if we were to use the ReLU function with this single layer, would we actually be squishing like data points from multiple classes onto the exact same point in feature space, and then they'd be impossible to distinguish at that point. That's absolutely true. So for that data set, you would potentially need either like additional layers or a different activation function to try and ensure separability. Yeah. Okay. So, and actually that's so I'll kind of go forward. There's a demo that's really useful for playing around with this in your browser, which I'll point out. And so you could actually test, on that last question, like you could actually test a data set that's exactly of that form and try to understand how choices like the number of layers or the activation function that you're using, how that can affect the separability of the hyperplanes that are being learned. Or not just hyperplanes, but the decision boundaries. So one thing, though, that's kind of worth thinking about is that actually, so like the number of layers that we're using, it will directly affect the complexity of the decision boundaries that are being learned by our neural networks. So in this graph, what we're showing is for the same training points, which are the circles within the 2D spaces, if we were to train models with different numbers of hidden units, so like different widths, how the decision boundaries would change. And so the takeaway is that as you add width within your neural networks, you can represent increasingly complex decision boundaries. And so this can be good in the sense that you can potentially have higher accuracy on more complex data sets, but it can also be bad in the sense that you might overfit. So for example, it might just be the fact that like in this lower example, like we have like a red training point here, that might just be a noisy example within our data set that we wouldn't want the model to we wouldn't want the model to really predict all of this region as red just because of that one training point. So potentially you could regularize your model by using a smaller width within your neural network. Alternatively, though, what's more commonly used as regularization is to just insert the regularization term like an L2 regularizer or an L1 regularizer within the network. The reason for that, generally speaking, width is an inherent regularizer, but usually it's not a tunable, like usually in practice you would instead use like L2 and L1 within your cross-validation because L2 and L1 can be, it's a continuous value. So for cross-validation you can get sort of more, you can get slightly more control about how strong of a regularization term you're using versus using like the specific architecture. Although inherently the architecture is a form of regularization, so it's worth thinking about. Within this web demo, you can also play around with the regularization, so you can change the lambda term. And so, for example, in this case, you can see how as we increase lambda, it's enforcing our neural network to have these smoother decision boundaries, which can potentially ignore outliers like maybe this green point, which would otherwise be used and potentially overfit by our model. Okay. Okay, so the next topic that I'll talk about is this notion of universal approximation. So you'll see references to universal approximation. It's a property of neural networks that's a good motivation for why we're using them and why they've been so successful. But I will caveat this discussion with the fact that we're going to be focusing in this class more on the practical application of neural networks and less on the theory. So this is just a high-level I would say somewhat informal discussion of this property of neural networks. So there's a lot of, so with this statement that a neural network with even just a single layer can approximate any function from Rn to Rm with arbitrary precision, like there's a lot of mathematical caveats that go along with that. If you're interested in the theory, I would recommend probably looking more towards the classes within the math department. We're going to be focusing on this class on the practical applications, but we should be aware of this because this is a great motivation for why we should use these functions, why we should be interested in them. Because if we can represent potentially any function from Rn to Rm, that's a huge set of functions that we might be interested in. And so it indicates that neural networks are very powerful tools for us. So let's look at how it is we can show that a neural network is a universal approximator, a universal function approximator. So let's take an example where we're trying to approximate some arbitrary function from just the real number line to the real number line. So the function maps from the space of R to the space of R. And we're going to use a two-layer ReLU activation function network to try and show this. So the way to read this graph here is we're showing that, let's say we have our input x, which is just a single number. It's going to have a hidden dimension, in this case, of 3. So we have like this weight 1, weight 2, weight 3, which will just scale our inputs to form H1, H2, and H3. followed by an activation function, which is ReLU, and then we'll have that second layer, which will have weights U1, U2, U3, which will be summed after multiplying by the hidden dimension to form our output scalar value Y. So stated then mathematically, so to get our hidden values, we're applying ReLU after the input. Oh yeah, and then we have a bias term which is not shown in the graphical representation, but is included as well. So to start to build up to this idea of how it is we can approximate any function, one thing you can do is you can sort of re-represent the output just using algebra in this form. But I'll kind of move through more of like a graphical interpretation of what this looks like. So let's just say, for example, that we wanted to approximate the function which is shown here. So this sort of bump function, or this sort of step up and step down function. We can actually do this using our two-layer ReLU network. And so to see how it is we can do that, the first thing let's think about is, so just to describe what this function is, let's say that this function that we're trying to represent is 0 everywhere up until the portion of the input which is S1, and then we have a linear slope of M1 up until some height which is what is it, M1 times the step between S1 and S2. So at S2 then the function becomes constant at that fixed height before then having a negative slope downward of slope M2 until the point along the input of S4, and then it's 0 onward. So if we think about how we could represent this with our two-layer activation function, or our two-layer ReLU network, let's say that we could first take, if we know what this slope is M1, we could scale just a ReLU activation of the input subtracted from the point at which the slope starts to activate, and that would produce this output here, which would at least be, it's essentially just ReLU that's shifted forward by S1. So that will now cover, assuming we just had that portion of our network, that would cover correctly all of the real number line input up until point S2. So at that point, what we would want to do is sort of counteract this positive slope, which we're going to be getting from our first component. And so we could imagine having another oops, I went too far. Another ReLU function, which is now has a negative slope of M1 applied to like this max operation. And what that's doing now is kind of counteracting the positive slope from our first hidden channel. And that's going to result now in, let's say, a function that is 0 up until S1. It has a positive slope of M1 up until S2, and then it's going to be constant forever. So now we have to handle this like downward bump. So to do that, we can do kind of the same idea. So we could have a function, assuming we know what this M2 slope is, we could have this third component, and then the same idea is like to counteract then the negative slope of this third component that we introduced, you could have then like a fourth component. So if you want to like work through the details of that after lecture, that's probably a good exercise. For the sake of time, I'll kind of step forward and point out that this is like a simple example of just how we could represent one bump, but you could imagine if you were to make the argument that if you kept adding hidden channels, you could keep sort of handling these, you could keep sort of adding bumps within your representation, and eventually, kind of in the limit, I mean, I'm getting hand wavy, but in the limit, you can imagine with enough of these bump representations, you could start to represent continuous functions, which could be arbitrary based on the height of the bump with respect to one another. So this is very hand wavy. For more detailed, for a more detailed description of this property of neural networks, there's a link on the calendar to chapter 4 of Nielsen, where they go into more detail about this property. From a practical standpoint, though, the main takeaway is that this property of neural networks is very powerful. It's a motivation for why it is we should be interested in them, because they can represent arbitrarily complex functions, assuming that we have a large enough network. In practice, though, this is not necessarily what our neural networks are going to be learning. So in practice, like the actual decision boundaries of our networks, we shouldn't think about in terms of these bumps, but this is an intuitive description of this property. The other thing that's important to remember is that while this universal approximation theorem is the case for neural networks, it doesn't tell us for a given problem that we're interested in how many hidden units do we actually need to represent some given function to arbitrary precision. So in addition, it doesn't necessarily tell us that if we train a neural network with stochastic gradient descent or some other optimizer, that will actually arrive at an arbitrarily precise approximator of the function that we're interested in. Nor does it tell us like how much data we would need combined with the optimizer to train the function to some arbitrary precision. So this is it's a property that's very motivating for us, but it doesn't necessarily give us tools that we could implement in practice to decide when we're going to achieve some level of desired precision or with what optimizer and so forth. But nonetheless, it's a very interesting property. Okay, so with just a few minutes left, I just want to briefly make a couple of points about convex functions. In particular, I'm probably going to kind of go fast through this and then leave a little bit of time for questions. The main point that I want to bring up, though, so all these slides I'll leave up online. The main thing, though, I want to bring up is the fact that, not that far, is there's a concept that you'll see referenced when looking at neural network literature, and in particular with literature within optimization, which is that when we're trying to optimize a convex function, generally speaking, we have optimizers where we can prove theoretically that we'll have convergence properties or we'll achieve potentially global minimum solutions to our optimization problem. So this is really nice because if you recall from the last lecture, the training of all of our neural networks is ultimately an optimization problem. So it would be very nice if the loss functions that we have for training our neural networks were convex functions, because we could potentially guarantee that we'll find the optimal parameter setting for our neural networks. The downside, though, is that generally speaking, oh yeah, and so as a nice example is that like linear classifiers are optimizing a convex function in the cases that we've looked at. The downside, though, is that for the problems that we're going to be looking at for deep neural networks, and a lot of the essentially all state-of-the-art deep neural networks, they don't use convex loss functions. They're non-convex functions, and we can't prove with guaranteed with theoretical guarantees that the resulting solutions to our optimization problems in the case of deep neural networks are globally optimal or that will always achieve convergence. So this is something to be aware of and is an issue that will kind of continually come up. Often we have to be satisfied with locally optimal or even not locally optimal solutions to our optimization problems in deep learning. And so there's some more details on the slides, but the main takeaway is that most of the neural networks that we're going to be using are trying to solve non-convex optimization problems where we have, generally speaking, no guarantees about the convergence properties. So it's a really hard problem to train deep learning. If you're interested in trying to establish theoretical guarantees, like that is an active area of research. So in particular, when you have like safety critical applications and you're trying to apply deep learning in them, generally speaking, whoever's on the other end who's depending on the deep learning solution, they would really like theoretical guarantees. So there's a lot of interest in trying to establish these for a lot of problems in the real world, but it's an open-ended problem. So if you're interested in research, that's one area that you could go for the final project. Okay, so just in the last couple of minutes here, a summary of what we've been talking about. So we saw how feature transformations combined with linear classifiers could allow our image classification techniques to start handling nonlinear decision boundaries and modeling nonlinear decision boundaries. And we saw how neural networks can act as a learnable feature transform for these complex data sets that we're going to be looking at in this semester. And in particular, then we defined our fully connected neural networks. In particular, we focused most of the discussion on two-layer networks, but we saw how that could extend to deeper architectures, and how, and then also how like the neural networks are using multiple templates within the decisions that it's trying to use for its classification. Having said all of this, now the next question that we should start to be thinking about is how can we actually start applying stochastic gradient descent and some of the optimization algorithms we looked at last time to these much more complex functions? Because if we're going to want to train these much more complex functions, we're going to need efficient algorithms that can compute the gradients with respect to all of these potentially deep parameters within the network. And so the algorithm that we're going to be looking at next time is called backpropagation. That is going to be an efficient algorithm to ensure that we can tractably compute those gradients. So with that, I'll stick around to answer any questions, but I will see you next Tuesday, and we will have a quiz next Tuesday.